Continuing on with class 18, here's some more examples. Here's one from Bornacki. A window-mounted air conditioning removes 3.5 kilojoules from the outside of a home using 1.5 kilojoules work input. How much energy is released outside, and what is the coefficient of performance? I don't think there's any Carnot action in this particular problem, so don't know why I didn't include it in there, but we could. No, we don't know the temperatures, so we need to know the temperatures really to do the Carnot thing. But anyway, we can get the coefficient of performance already listed right here for a refrigerator is QL divided by work, and I could even put in if you want. And it says that it removes this, right? So that's the QL. They're already telling us that. So 3.5. These are kilojoules, so it's not. It's a certain amount of heat, not a heat rate. And this is 1.75, right? So we get a exciting 2 is our coefficient of performance. And so we want to know how much heat is rejected. It's a simple conservation of energy equation here, where we have in minus out, so that's how much is rejected right there, minus amount of work put into it. Or if I want to write it in other terms, this is the QH minus the QL minus the W. So they're asking sort of how much heat is released outside. That's going to be QH is equal to QL plus W. And so just 3.5 plus 1.75, so QH is 5.25 kilojoules. Kind of a boring problem. But we will continue on with some more exciting problems. Here is problem 524. All those marks on that desk. An industrial machine is being cooled by 0.4 kilograms per second of water at 15 degrees Celsius that is chilled from 35 degrees Celsius by a refrigeration unit with a coefficient of performance of 3. Find the rate of cooling required and the power input to the unit. So we have this water flow, the water, of 0.4 kilograms per second. The if I were to draw maybe a heat exchanger, something like that, I don't know, where this is T in and this is T out. And this is the flow coming through there. T in is equal to, excuse me, my bad. You read the problem a little bit more. It's cooling it from 35 to 15. So I guess this is in, right? And this is out. My bad. In is 35. 35 degrees Celsius, and T out is equal to 15 degrees Celsius. And notably that water has a specific heat, 4.18 kilojoules per kilogram degree Kelvin. So this is going to be the change in enthalpy that's going to take place across here. So there's going to be, we're removing, however we're doing it in there, probably through another fluid, we're taking out energy here. So we go Q out, and this is going to be on the, there's also Q low, by the way, in whatever refrigeration system they're dealing with here. M dot Cp delta T, or 0.4, 4.18, and we don't need to change the Kelvin because it's a temperature difference, so it's going to be 35 minus 15. And so the L is going to be 33.44 kilowatts, right? Because it's kilojoules, kilograms per second, so that the kilograms get away to the kilojoules per second, and degrees, so we're left with kilojoules per second, so that's a kilowatt. And the coefficient of performance for a refrigerator here is the Q dot L over the power in. So we can find what the power in is going to be. And that's going to be Q dot L over COP. And they gave us the COP. So it's 33.44 kilowatts divided by coefficient of performance of 3. You can expect 11.15 kilowatts of power to be required in order to do this. If you're now, I don't want to say this. I'm going to keep on going to the next example. Let's go to the next example here. All right. So here's like where they're asking three things, three problems in one. And they say, assume that a cyclic machine that exchanges 6 kilowatts with a 250 degree Celsius reservoir and has this QL of 0 kilowatts, so it doesn't do anything, and it just produces this work right here. So it doesn't lose anything, right? It's not rejecting. It's a machine, it's not a refrigerator. I need to make that clear. We were just doing some refrigerators, but now we have a machine. And so we go from, we have a 0 loss. And so here's our main equation. Well, let me put our main equation, the conservation of energy. We'll say 0 is equal to QH minus QL minus work out, right? So, and Q is exchanged with a 30 degree ambient. What can you say about this process in the two different cases right here, A and B, if the machine is a heat engine, and then repeat if it's a heat pump? So here is a heat engine. And what can we say about these two things? So A, Q dot L is equal to 0, and this is equal to 6 kilowatts. Well, you take a look at it and you go, well, it's not going to be possible because we can't. It defies some of our principles right there. I think it's either Clausius or the Kelvin Planck. I think it's the Kelvin Planck. Kelvin Planck says it's impossible to just move without having a low. You need a low rejection. You need to reject some heat right there, so it's not possible. You can't get all of the heat in, which is the, in this case right here, we're saying that the QH is going to be 6 kilowatts. So not possible because, and I wrote down that it was Kelvin Planck, so I couldn't remember which one was which. I should, but I didn't. And I think Planck has an extra C in it. I think so. Because of Kelvin Planck's statement. And of in here, because that's actually needed. And you can't have 100% efficiency because efficiency cannot equal 100%. Okay, I should write cannot. That does not. Can't. You can't have 100% efficiency. B, we have a situation where we have QL dot equals 6 kilowatts, and then the work's doing nothing. Well, yeah, you could have that, I guess, because why not? Just throw it all away. Because what you would be saying up here is QH is just going to be equal to 0 plus Q dot L. All right, so you'd have that 6 equals 6, and that's true. Where it is not true up here, but you could, I don't even want to say this right here. But it would be pointless, right? It says it's possible but pointless. Because why would you do that? you're just throwing stuff away. If we have it for a heat pump, all right, so here is our other perspective right here. Okay, so in our heat pump, do I want to say this right here? Yeah. All the signs switch, so it doesn't quite matter. But like for the in of the thing is going to be, yeah, so we have heat out. Yeah, that's what it is. Okay, so it'd be equal to negative is H, because now this isn't heat in. The high is actually the heat out right here. This is the heat coming into the house in a heat pump. And we're putting, the low is what we're putting into the engine. And that's requiring work to be in. See, yes, okay. All right, so that's this is the formulation that we would take. So you still have the QH is equal to QL plus W in. Right, it's just as you would up above, but now we're just in a heat pump because it's the situation. So A, is it possible to have the H be equal to, like as we mentioned, remember that A was the condition where the low rate was 0 right here, so that's going to be 0 plus 6, right? So we have 6 plus, yeah, so this is what's coming in, 6, and we said that we wanted 6, so we were fine. So this is yes, possible, but the coefficient performance, as they like to put onto the thing, is okay, and this is the coefficient of performance, and they go beta prime for the coefficient of performance of a heat pump is going to be H over this, and it ends up equaling 1. So that's not a good coefficient of performance of a heat pump. B. So what you're basically doing is you're not pulling heat. In this one, you're not pulling heat from the outside. You're actually, what you're doing is you're just taking an engine and you're dumping the engine's work into the room, right? You're heating the room with just, taking the engine. It's not exhausting it, but you're basically, that's what you're doing, is you're turning all that power from the engine just into exhaust heat, essentially, into the room. And then the other condition right here, you could go QH, and it was going to be equal to, now this is 6, but this is going to be QL, and then plus 0. But this is not possible because you're going to move from a high to a low, right? There's no work coming into this thing, but you're going to be moving, you're going to be moving the low temperature into a high temperature, coming that direction right there without ever having any work. So this is not possible because it violates, did I spell that wrong? Violates the Clausius statement. And really that should be probably, we should be talking about that in the previous class, in class 17, I think so. So let's see, we're 14 minutes in. Is that the last one? I think that might be the last one. That's the last one. Okay, good. I like this class. This class wasn't any fun. I don't like this chapter, to tell you the truth, but I want more practical stuff. Let's see if the next class does any better. All right, goodbye.